we are going to see how we can approach the definition of a group by very simply understanding the concept of the symmetries of an equilateral triangle. So let's move on to the say. Symmetries of an equilateral triangle. We know that symmetrical objects are treated as objects of beauty. Okay. Whenever we are thinking about a culture, a tradition, a society, a spirituality group, a religious group, all of them are very fond of regular patterns as well as symmetrical objects. Even symmetry links are connected with chemical reactions, scattering of elementary particles. A musical score, for example, sa re ga ma pa da ni sa ni tha pa ma ga ri sa. Even in that, you have a symmetry. One goes up, that goes down, right? So you have a symmetry there. And even in the evolution of the solar system, and even in mathematical equations, we are following symmetry. Once the word symmetry is mentioned, a mathematician always think about a mathematical structure called a group. So, how we can conclude the definition of a group from the symmetries of an equilateral triangle? Let's find out. Yes, this is an equilateral triangle, right? You have three sides, all the three of them to be having equal length. Similarly, all the three angles of the equilateral triangle, all of them are 60-degree because what we do is we divide uh, the whole of the angle divided by 3 and you get 60. 180 divided by 3, that will be 60. So that's an equilateral triangle. So our basic aim is to present the idea of a symmetry of an equilateral triangle, which will definitely help us to introduce the study of algebraic structures called groups. So let's observe the equilateral triangle given below. You have to also note the angles, the vertices which are denoted by alpha, beta and gamma. Also you have to look at the median lines. These are median lines and the angles which are specified at the centroid of the triangle. Okay, so you have the angles to be 360 divided by 3, you have 120, 120, 120, and all of the angles, as we earlier said, all of the angles will be 60-degree at alpha, beta and gamma. So this is an equilateral triangle. So what are symmetries? So the basic aim is that we have to check which type of motions or which all motions are there which can bring the triangle back to its original position. Vertices, the name of the vertices can change, but the shape of the triangle should remain as such after the motion, after we do the motion, right? So that is our basic aim. We have to identify all such motions which are possible on this equilateral triangle. So we are going to talk about the first motion. So you have the equilateral triangle sitting here, you have the vertices alpha, beta and gamma. The first motion you can denote it by E, and this motion is nothing but you can call it the lazy motion because we are not going to do anything at all on this equilateral triangle. So you are keeping the triangle as such. That is, we are not changing anything. Okay. So you can notice the labeling of the corners. After doing nothing, the labeling will be the same as alpha, beta and gamma, right? The top vertex will be alpha, the vertex to the left of the bottom part will be beta and the vertex to the right of the bottom part will be gamma. Okay, so we are not going to do anything and that is the first motion, and you can denote it by the letter E. And also note that the equilateral triangle, if we are going to rotate the equilateral triangle around 360 degrees counterclockwise, then also the triangle will remain as such. Okay, you have to just keep that in mind. We might have to use that point later. Okay, so you got the first motion. Now you're going to get the second motion. The second motion will be rotating the equilateral triangle about 120 degree. So that means you're going to flip, or you're going to rotate the equilateral triangle counterclockwise like this, 120 degree. So when you have rotated the same, so you get the change like this. That is, when you are doing a 120-degree rotation, your alpha is going to beta, right? The alpha is going to beta, beta is going to gamma, and gamma is going to alpha. And at the end, you're going to finally get this equilateral triangle. The shape is the same, but you have differences at the vertices. Instead of alpha, you have gamma here. Instead of beta, you have alpha here. Instead of gamma, you have beta here. Okay. So you call it as the second motion, and you can denote it by a small letter A. And yes, as we said, the equilateral triangle is being rotated 120 degrees counterclockwise, and we have noted the new locations of the vertices alpha, beta, and gamma. So that's an end to the second motion. Now the third motion, what you're going to do is we are going to rotate the equilateral triangle around about 240 degrees from the center. So you have this alpha will move to gamma, gamma will move to beta, and beta will move to alpha. See? This is the final position the equilateral triangle will end up with, and you can see that the shape is not distorted, but the vertices, the labeling have changed. So here the triangle, after being rotated 240 degrees counterclockwise, you are getting new positions of vertices, which are alpha, beta, and gamma, coming like this. On the top you have beta, on the bottom left you have gamma, and the bottom right you have alpha. So that's an end to our third motion. And then let's see what are the next motions. Now what you're going to do is you are going to drop a perpendicular from the top vertex alpha uh, to the bottom, to the base of the equilateral triangle, and you're going to uh, have to treat that line as an axis, and you're going to flip the equilateral triangle about that axis. Okay, so that means the alpha is going to remain as such here, but this gamma and beta will be flipped, right? So what you get at the end is like this: the alpha will remain as such, beta will be changed to gamma, and gamma will be changed to beta, right? So that is the fourth motion we are talking about, and that you can denote it by capital X. So the triangle formed is by flipping about the axis through the upper vertex. Note the new positions, and we have discussed the same. So that's an end to the fourth motion. Let's see what is the next motion. So here what you're going to do is you're going to drop a perpendicular from the bottom left vertex beta to the opposite side, and you're going to use it as an axis, and you're going to flip the equilateral triangle about that axis, and you know that beta is going to remain as such, and alpha and gamma will be flipped about the axis. So what you get is the triangle sitting here. So you have the beta to remain as such, and alpha is changed to gamma, and gamma is changed to alpha. And that is actually the fifth motion, and it is denoted by capital Y. The triangle, after being flipped about the axis through the lower left hand vertex. So beta was the lower left hand vertex, and we have noted the new positions of vertices alpha, beta, and gamma. So that's an end to the fifth motion. It is denoted by capital Y. And the next motion is by forming the line from the bottom right vertex to the opposite side, the perpendicular, and treating it as an axis. You're going to flip this alpha and beta, and you know that the gamma will remain as such, and the alpha and beta will be flipped. So instead of alpha, you have beta here. Instead of beta, you will have alpha here. So you can call it as a sixth motion, and it is denoted by capital Z. So this is formed by the triangle being flipped about the axis through the lower right hand vertex, and we have noted the positions of the vertices alpha, beta, and gamma. So overall, you have talked about six motions. Okay, the six motions are, the first motion is the lazy motion, as we have talked about. It is the doing nothing. We do nothing on the equilateral triangle. And then what you do is you rotate 120 degrees counterclockwise. Then you rotate 240 degrees counterclockwise. And the fourth one was flipping about the symmetry axis through the upper vertex. The fifth one was the flipping about the symmetry axis through the lower left hand vertex. The sixth one was flipping about the symmetry axis through the lower right hand vertex. So there are other motions. We can think about other motions definitely, but all of the other motions that come into our mind on which are the motions on equilateral triangle, which makes it remain unchanged after the motion. All of those motions, all of such motions are equivalent to the six motions which we have listed above. For example, as we said earlier, we had talked about rotating the triangle 360 degrees, and we said that it is equivalent actually to the motion of doing nothing. We said to note about it, right? So that is equivalent to doing nothing. So similarly, many other motions that come into our mind are equivalent to those which I listed above, and uh, we are keeping a rotation counterclockwise, using the counterclockwise rotation as a positive orientation. And that's why the orientation, so that the orientation of the triangle is unchanged. That's why we always use the counterclockwise rotations on the equilateral triangle. So we got a set of motions, right, on the equilateral triangle, and we denoted them by E, a small letter E, small letter A, small letter B, then capital letter X, Y, and Z. So you have six motions. You make it into a set, okay, and this set you can denote it by D3 or S3 because you are denoting it by 3 because you are dealing with the triangle, and the equilateral triangle has three vertices. So that's why I'm calling it D3 or S3. And usually it is called as the dihedral group or the symmetry group on three vertices. So now let's introduce an operation of performing one motion followed by other on the set. Okay, so you have six motions, and then you have to introduce an operation on this set such that one operation is followed by the other operation in the set. Okay, so as an example, let's see the motion A is followed by the motion Z. Okay, so the motion A, we know we rotate the equilateral triangle about 120 degrees counterclockwise. So when you do the counterclockwise rotation 120 degrees, you get the alpha to be shifting to beta, beta to be shifting to gamma, gamma to be shifting to alpha. And after that shifting, you have to give the motion Z. So the motion Z was the flipping about the bottom right vertex, or about the axis at the bottom right vertex. So you already obtained the triangle after giving the motion A, and on that triangle you are going to flip about this axis, and that you are going to get the triangle which is sitting here, and this triangle is nothing but the flipping of the triangle at the axis from the top bottom vertex. That is flipping. You have an axis like this, and you're flipping beta and gamma. Okay, so that is actually the motion x. So what you obtain is, if you're applying the motion A on the equilateral triangle, and then you are applying the motion Z on the resultant equilateral triangle, you are going to get an equilateral triangle which is actually the motion uh, which is actually a motion among the six motions we are talking about. Okay, so you obtained A followed by Z to be to be the motion X. So similarly, you can think about all of the motions operated with each other, and you're going to obtain some things. Okay, so these motions form a group. So we are going to introduce what a group is. Using the operation of followed by, okay, you have a set and you have an operation followed by, okay, you have a set of motions and you identify that performing one motion followed by performing another motion is equivalent to performing one among the six motions. As we said, as an example, A followed by Z, you obtain the motion X. So performing two motions together is actually a performance of a motion among the six motions. Okay, so you call that as the operation, such an operation as a closure operation. Okay, and also you know that followed by is always an associative operation, because if you take a motion and then you take another motion, you operate them, and then you operate another motion, that is equal to, first you have a motion, you keep it there, take the other two motions, and then on the whole, use a followed by operation. You get both of them to be equal. I hope you got the point about the associative operation. And the doing nothing motion is actually a special element in our set, and that element is called the identity element, because operating the special element with other elements leave the other elements unchanged. Okay, and also each element has an inverse. That is, the inverse is an element that can undo the effect of the combination of another given element. For example, the doing nothing element is its own inverse. The rotating 120-degree motion is actually the inverse of rotating 240-degree motion, and vice versa. Okay. The three flip movements are their own inverses. Okay, doing the flip twice, you get the original equilateral triangle. So these four properties you get from the set of motions using the operation followed by is actually the criteria for forming an algebraic structure called group. And also the performance of motion one followed by another can be represented in a table like this. See, the identity element E or the special element E applied on any other element inside any six elements, six motions in the set, you get the same elements, and here also like that. And if A is applied on E, you get A is applied on A, you get B, A is applied on B, you get E, A is applied on X, you get Y, and so on like that. So, and usually this table associated with a group is called a Cayley table. The Cayley table, and you can remember this Cayley table by simply just matching it to a Sudoku. You might be very familiar to Sudoku puzzles, because if an element comes in a row and a column, that row and that column will not have that element again. That's how you play a puzzle of Sudoku. The same manner in a Cayley table, if an element comes in a row or a column, that element will not come in the same row and the same column again. Okay, so that's a Cayley table. And to conclude, we can now formally define a group as a set together with an operation which is actually a closed or the closure operation. The operation is closed, is a closure operation, and it is associative, it is having an identity element, and that every element has an inverse. That's how we end up by defining the simple definition of a group from the symmetries of an equilateral triangle. Hope you got this simple session and understood what it is. And thank you for watching this video, and hope this helped you in understanding the symmetries of an equilateral triangle and how it can be associated to define a group. So thank you so much. Have a great time.